Okay, so part two of the chain rule 2.4. We left off that last problem. I'll go ahead and I want to show you. So the graph of f of x is provided here, and notice that what the question was asking is find the points, right, where the derivative would equal 0 or not exist. And these three dots here are the points that are of interest to us. So let's start with when x is equal to 0, right? So what's the y value? Well, if you plug 0 in for your original function, you would have 0 squared minus 1. So that would be negative 1. Negative 1 squared is positive 1. And of course, the cube root of 1 is 1. Now, if you plug a negative 1 in, you would end up with negative 1 squared, which is 1. So, and that would mean you would have 1 minus 1. So that would be 0. And then if you plug a positive 1 in, you would also get 0. So these are the 3 points that, and you can see that. Let's take at the point 0, 1. You can see how you would have a slope of 0 at that point. But if you recall in the pre 2.1 when I were talking about how derivatives can't exist at sharp corners, you would have a derivative that does not exist. The slope wouldn't make any sense at the points negative 1, 0 and positive 1, 0. Okay. So I know what you're thinking. So you're thinking, okay, so Professor, these chain rule, product rule, quotient rule, power rule, by themselves hasn't been super challenging. But how are you going to make it tougher on your test? Like, what do I need to be ready for? Well, the point of the lectures is not, for at least for these types of problems, is just to study the methodology and point out some traps to be careful of. It's in the textbook problems that you should start to tackle some harder problems. But to answer the question, although I don't consider this a tough problem, this is how I can make it more difficult is I can start to combine the rules, right? So for this particular example, you're going to need to use a product and a chain throughout the problem. So let's begin. So we have our function, and I'm hoping as of right now you can notice that this is a product of two different functions of x. So that automatically tells me I'm going to need a product rule. Now, I might not notice the chain yet. So my course of action is I first say, can I rewrite this to make my derivatives easier? Well, I can. I can rewrite f as x squared, and instead of having a square root, I could have 1 minus x squared to the power of 1/2. Okay? But let's assume that we don't notice a chain rule is going to be needed yet. So we just proceed as we would with the product rule. So again, continuing to use the same definition, I need f, g, f prime, g prime. So we start off with, we can let f be x squared. We can let g be 1 minus x squared to the power of 1/2. Now, when I take the derivative of f, I get 2x. But it's right here that you should notice that you're going to need a chain rule. Okay? So this part right here, in order to take the derivative of g, I'm going to need a chain. So I'm going to come off to the side. All right, I'll come back to that product rule, but I need to figure out what g prime is. So I'm going to come off to the side. All right, so let's go ahead and write. So if we have g being equal to 1 minus x squared to the power of 1/2, then you remember how to do this. We need to choose a good u, and then f of u, and then continue. So if we let u be 1 minus x squared, then f of u would be u to the power of 1/2. Now let's take the derivative of f with respect to u, which would be 1/2 u to the, well, if I have 50 cents and take away $1, I now have negative 50 cents. All right, and last thing is let's take u prime. So I've made this mistake before, even on the board, even when the answer's staring at me. Be careful with that negative symbol. So when I take that derivative of u, it should be negative 2x. Okay, so all of this work so that I can establish f prime of u multiplied by u prime. So let's put everything in the right spot. So f prime of u would be 1/2 u to the negative 1/2 times u prime, which is negative 2x. I'm not going to forget to plug the 1 minus x squared back for the u. So that becomes 1/2 times 1 minus x squared raised to the power of negative 1/2 times negative 2x. Okay. So I realized that was a lot of work, but I needed this g prime so that I could finish up my product, right? That detour was just so that I could find g prime. But now that I found it, well, let's just go ahead and write that product rule. Again, I'll have to call upon memory. F prime times g plus f times g prime is, I'm sure, what I used. And now let's put everything in the right spot. So f prime, so that would be 2x times g, which would be 1 minus x squared to the power of positive 1/2, plus, let me give myself a little bit of space here. All right, so plus f, which is x squared, multiplied by g prime, which is the mess that we have down at the bottom. So if you want, you can clean this up right now, or you can plug it in and then clean it up. I think because I'm starting to run out of space in the top, I'm going to go ahead and say if I take half of negative 2x, that would just be negative x. So that would be, let's make sure I give myself enough space down here as well. So that would be negative x multiplied by 1 minus x squared to the power of negative 1/2. Okay, so this here is what I'm going to insert, and I'll keep the same color. So negative x times 1 minus x squared, all raised to the power of negative 1/2. That's my g prime. All right, so this is one of those problems that I'm going to have to erase the work for my chain at the bottom to help finish this. Again, just to reiterate something, my engineers, my science people, this is the derivative. Now, it's sloppy. It's in form, it's sloppy. But this is your derivative. We just need to clean it up and offer a better product. So let me give myself some space. The reason why I say to my engineers, to my science people, is because if all you cared about was, let's say, the velocity 2 seconds after launch, then you could just plug 2 in the way it sits. It just so happens that it's a different game in your science classes than in your mathematics classes. In the mathematics classes, you are making an argument in which you need to justify all of your steps. And a lot of times in your science classes, this is just a tool to get to an answer that you need. So what I'm going to do is I'm going to get rid of all these parentheses that are cluttering, and I'm going to go ahead and multiply x squared times negative x, which is negative x cubed. So I want to do all of this in one swoop here. So f prime of x, let's rewrite this without all of these parentheses. So that's 2x times 1 minus x squared to the power of 1/2. And that's going to be, it was plus, but now since I'm doing x squared times negative x, that's going to be minus x cubed times, I'm going to use, since I have multiple, no, I'll just use parentheses, times 1 minus x squared to the power of negative 1/2. All right, so to appease your current professor, the only thing that I'm worried about is that you rewrite your answers without these negative exponents. So let me go ahead and do that now. So I'm going to move the entire base, and the base is 1 minus x squared. All of that is raised to the power of negative 1/2. That whole base is going to move, leaving me with x cubed over, here we go, 1 minus x squared to the power of positive 1/2. Okay, so your current professor, well, if you have me, maybe at some point if I decide to release these videos throughout YouTube, obviously other students wouldn't have me, but I am good at this step. I would, if I'm you, practice combining those, because I could easily take this same question and state it as, what would make the derivative, what points would the derivative equal 0, or when would the derivative not exist? And that would force you to combine your two terms. So it probably is a good idea. I'm going to just write, what I'll do for you is I'm going to write what it would look like if you were to combine all your terms. And you should, on your own time, practice that little bit of algebra to see if you can simplify it, okay? So this is, if you were to look this up in the back of the book, I would assume your answer would look something like this. X times 2 minus 3x squared over the square root of 1 minus x squared. Now this is not too bad if I wanted to set the derivative equal to 0, or if I wanted to figure out when the derivative does not exist. I've already answered this and pointed this out, but just remember, if you want the derivative to equal 0, if you want a fraction to equal 0, make the numerator equal 0, or set the numerator equal to 0. Okay. What I want to do now is focus a little bit on trigonometric functions in the chain rule, and I can make this very simple. You can read through this if you'd like, but it's very simple. You're going to need the chain rule if you alter the angle. Does that make sense? So if I had sine of x, no need for a chain rule. If I had just cosine of theta, no need for a chain rule. But as soon as you start to change the angle, right, which would potentially change the period of your function, now you have, since you've altered the angle, you're going to need a different rule for finding the derivative. But we're not going to introduce any new notation. We're going to continue with f prime of u multiplied by u prime. Okay? So in this case, let's start with a. I'm recognizing that I need a chain rule, and I'm going to allow u to equal 2x. It's easy when you're watching a lecture called chain rule to know that you're going to need the chain rule. It's much harder when you have a test with 15, 20 questions all mixed up, and something like this pops up, and you could easily forget that requires a chain rule. Okay? So if we allow u to be 2x, then f of u would be sine of u. And as you recall, I need f prime of u, and I need u prime to finish this up. So f prime of u, well, the derivative of sine is cosine. And then u prime is derivative of 2x is just 2. So to finish this up, plugging everything in for my chain rule, I would have f prime, which is, I'm going to now start to just go ahead and plug in for u. Okay? In other words, I'm going to go ahead and do that substitution where I plug 2x back for u in this step. So you would end up with cosine, f prime of u would be cosine of 2x, and that would be times u prime, so times 2. So y prime is equal to 2 cosines of 2x. Okay. Let's go ahead and do part B. So I'll work up here. So if for part B, I would let u equal x minus 1, then f of u would be cosine of u. F prime, well, the derivative of cosine is negative sine, and u prime would just be 1. Okay, so f prime of u times u prime, plugging in back for x minus 1 back for u, I would have negative sine of x minus 1. That would be f prime, and that would be times u prime, which would just be times 1. Okay. So last one, tan of 3x. We would let u be 3x, and I'll go ahead and write all this out. So that would f of u would be tan of u, f prime, and u prime. So remember, so either through memory or formula sheet, looking it up definitionally, f prime is the derivative of tangent is secant squared. Okay, and the derivative of u is 3. So all said and done, f prime of u times u prime, I'm going to get secant squared, but instead of having a u, I'm going to go ahead and put my 3x back in, and that's times u prime, so times 3. All right, so this is my answer, 3 secant squared of 3x. I want to state something that if you had a good, so this is y prime, this is y prime. If you had a good pre-calc teacher or trigonometry teacher, this is, by the way, I need to erase that. This looks horrible. Then this is going to be something you already know, but if it's been a while since you've had trigonometry, or maybe it was hard, the subject was hard for you, either way, I want to point out something that's silly but happens enough to point out. So I've seen quite a lot of students right here take this 3 and distribute it inside the angle, to the angle inside your function. And I'm telling you, you do not do that. This, what's inside here is sacred, if you'd like. It's off limits. So this 3 just becomes the coefficient. All right, so where do we go from here? So I have, I want to show you a problem where you need to use the chain rule multiple times, because that does happen. And then I want to actually do a few application questions so that we can see some of the why behind this how. Okay, in other words, the word problems at least tell us the value of this procedure. So let's start. We have f of t is equal to sine cubed of 4t. And I'm going to rewrite that as f of t, well, sine cubed of 4t. What that means is you have sine of 4t raised to the power of 3. Okay? So at this stage, you might not notice that you're going to need the chain rule more than once, but let's go ahead and just jump in and get started. So we start off with, let's label u. In this case, we would have sine of 4t, and then f of u would be u to the power of 3. Then I need f prime, and then I need u prime. I'm going to go ahead and do u prime. I'm sorry, f prime first, of course. So the derivative of u cubed with respect to u would be 3u squared. But it's at this step right here that you should notice you need a chain rule again. Right? Because let's think about it. You want to take the derivative of u. Well, what is u? U is sine of 4t. But remember, you've changed the angle. So we got to come down here, and I'll alter the color here. So sine of 4t, now that's our function. I won't label it. I could call it h or g or something if you like, but in order to take the derivative of that, I'm also going to need a chain rule. So back to it. So let u be 4t. F of u would be sine of u. Now I need f prime and u prime. So the derivative of sine is cosine. And the derivative of 4t with respect to t is 4. All right, so I have all 4 of my pieces. So that means I can go ahead and use that formula for the chain rule. The previous problem, I'm missing the 4th piece, so let's go ahead and finish this up. So f prime of u, that would be cosine of u, but I'm going to go ahead and plug back in the 4t. So cosine of 4t. And then that's going to be times u prime, which is just 4. So I end up with 4 cosine of 4t. Okay, now this was just an intermediate step because I now know what u prime is in the above equation. So let's write that. So u prime is 4 cosine of 4t. Now I have, at this stage, I have all 4 parts. Let's plug everything into the chain rule and we'll be done with this problem. So 3u squared is f prime of u. Let me go ahead and plug back in for u. So that would be 3. U is sine of 4t. And that's 3u squared. So 3u squared. Multiplied by u prime, which is to multiply by 4 cosine of 4t. All right, well, so this is my derivative. So this is f prime of t. And I'll clean it up, f prime of t. The only thing that I can do is multiply the 3 and the 4. There's nothing else to do here. So 3 times 4 is 12. And I'm okay with keeping it as sine of 4t squared, but normally we write, just so we don't clutter things, sine squared 4t times cosine of 4t. And since all we were asked was to find the derivative, voila, we're done. There's no need to go any farther. So now, what I want to do from here is we'll do a couple easy, the chain rules part will be easy for these next 2 problems. But let's actually find some value here. So let me read the question. So it says, the number n of bacteria in a culture after t days is modeled by the following function. So notice that this is the variables here, or the variable here is t, and that is time in days. And if I just plug a value of t, what will come back out is the number of bacteria in some culture. Okay, so let's make sure you understand. If this were pre-calculus, I would say something like, how many bacteria were there in 1 day? Or how many bacteria after 2 days, or 3 days, or so forth. But this is not pre-calculus, so we're not just plugging in here to get a number. What we want to know is we want to find the rate of change of n with respect to t. In other words, let's assume for a second that the number of bacteria is growing. But is it growing the same rate 1 day into the experiment as it is 2 days into the experiment? Or is the rate of change itself changing? So when you read rate of change, you should be thinking derivative. So in other words, I'm going to need n prime. Okay, so to do this, what I would do is I would distribute this 400 just to make life easy on me. So now I would have n is equal to 400 minus, well, if you do 400 times 3, I would have 1200 divided by t squared plus 2 squared. Okay, so that makes things a little bit easier. I'm going to go a little bit farther. Since I am going to have to use the chain rule, let's rewrite n as 400 minus. Now I'm going to take this whole denominator, which is raised to the power positive 2, and I'm going to bring it up to the numerator. When I do, does that make sense that if it's to the positive 2 in the denominator, if I bring it up to the numerator, it should be to the power of negative 2. So that gives me 1200 multiplied by t squared plus 2. Now it's raised to the power of negative 2. All of this work up front in the problem to make this derivative as easy as possible. But there's nothing else left to do except to take the derivative. So the derivative of 400 will zero out. And I'm going to go ahead and remember, you would just go through, you would need u, then f of u. You would need to go through this work. So in this case, u would be t squared plus 2. F of u would be 1200 u to the power of negative 2. And then I would need f prime of u and then u prime. So u prime would just be 2t, and f prime of u, oh, well, what do we got? We got 2400 negative, let's see here. Yeah, it's going to end up being a positive because we have a negative in front of that. So I've written it this way, so let me just tackle it this way. So this would be 2400 times u to the power of negative 3. Okay, so let me now just get to n prime. So this would end up being, I should have put a negative here. My apologies. It's going to end up being positive in the end. So that's negative 2400. So, all right, so because you already have a minus symbol in front of the 1200, that minus negative is going to end up being positive 2400 times t squared plus 2 to the power of negative 3 multiplied by 2t. All right, so let's clean that up. So if I do 2400 times 2t, that would be 4800t, and I can go, since I have a negative exponent on this base, I can move all of that to the denominator. So let's start with the 4800t. All right, and now let's take the t squared plus 2 to the power of negative 3 and move all that to the denominator so that we have t squared plus 2 to the power of positive 3. Okay, so at this stage, you have appeased your professor, except you're not done with the problem because you weren't just taking the derivative. The derivative is now a tool. And what do we want to know? Well, we want to know the rate of change in the number of bacteria with respect to time. And they give you the time. So 0 days into the experiment, 1 day into the experiment, 2, 3, and 4 days into the experiment. Part F is, well, what can you conclude from all of this? So A, B, C, D, E. This is just plugging in a time into the derivative. So this is, I'll write it as N instead of F. So this is N prime of 0, N prime of 1, N prime of 2, N prime of 3, and N prime of 4. Okay, so if you plug 0 in to your derivative, you end up with 0. And that makes sense. At the start of the experiment, the rate of change and the number of bacteria should be 0 because you have not allowed enough time for the number of bacteria to change. So you can't measure a change if no change has happened. N prime of 1. Now, again, you should use your calculator and double check. These are going to be just approximations, but just double check that I did my arithmetic correctly. I'm getting 177.8, 44.4, 10.8, 3.3. All of these are the change in bacteria per day. All right, so 1 day into the experiment, notice it's a positive number, so that means the bacteria is increasing, and it's increasing at 177.8 bacteria per day. 2 days into the experiment, the population is still increasing, but now it's only increasing at 44.4 bacteria per day. And so forth. So part E just basically, so part E, no, part F just asks, can you make a conclusion? What can you conclude? In other words, the way I would interpret that question is, as time continues to pass, right? So you could think of it as letting t approach infinity, meaning as time continues, the population is what? Well, you could say not the population, but the rate of change of the population. So n prime of t is approaching, well, the way we phrase it is, might be differently, but let's see if you and I agree that it just looks like as time goes by, there's less bacteria being added to our population, right? I mean, 4 days in, we're only getting 3.3 more bacteria per day. It appears that it's just starting to level off, right? There's some horizontal tangent that your population is approaching. You could think of it as there's some maximum population, sustainable population, something to that nature. How you word that is up to you, but it's, n prime of t is obviously approaching 0. Or if you wanted to, in terms of what can you conclude, well, maybe you conclude that there is some optimal population for this bacteria culture. All right, but this is fine. All right, now the last question for this section is, well, at least I think that if you've ever purchased a car or you are in the market for a car, I think you can appreciate this problem. Now, let me read, because this problem mentions a machine, but you can just as easily think about this as if you're purchasing your machine as a new vehicle. But it says, look, the model is the value, now we're going to let value be V, of a machine T years after it is purchased. All right, now when I read word problems, I stop whenever whenever I have to, especially at commas and periods, and I want to make sure if I have to take notes, I do. And but I don't want to keep reading unless I understand what I've read so far. So V is value, and T is time in years. Okay. Now, it says V, the value of a machine, V of the machine, T years after it's purchased, here it is inversely proportional to the square root of T plus 1. Now, in the beginning of your math studies, statements like that can be consuming, it can be confusing, but inversely proportional. So wait a minute. So the value V is equal to, well, it's inversely proportional to the square root of T plus 1. So I'm going to get back to this proportional, what that means in just a second. But inversely, so that would be, you would be thinking some type of multiplicative inverse, right? Some reciprocal. So inversely proportional to, and we know how to write the square root of T plus 1. So over the square root of T plus 1. Okay, so now the question becomes, well, what goes in the numerator? So really quickly, when you read proportional, there has to be some constant of proportionality. They normally use we'll normally use a K to represent that constant. That proportional constant. So inversely proportional, so that's the K to the square root of T plus 1. So part A is actually already done. It says write V as a function of T. All right, let me finish it says the initial value of the machine is $10,000. Now, initial value would mean when you first purchased the car. I mean, not when you drove it off the lot or anything like that, but at time 0, at first purchase, here is the value. So in this case, you could set V to equal 10,000, but really what you're gonna find is, in this case, your K is just 10,000. Right? You could plug 0 in for T because that's the initial time, the initial value, and you could set it equal. Like if I plug 0, listen, I'll just do it because I don't want to. If I let V equal 10,000, and it's when I first bought it, so time is 0, then do you see how, well, it's just the square root of 1, which is 1. Do you see how K is equal to 10,000? Okay. So this is part A. Okay. So assuming that this modeled your vehicle purchase, what would this do for you? So let me go ahead and plug 10,000 in for K. And let me tell you what this would do. So if you wanted to, let's say you bought your car for $10,000, and this is how you would model its value. So at time 0, it's worth 10,000. 1 year later, you could plug a 1 in for T. You could figure out the value. 2 years later, 3 years later. But what if you want to know something different? What if you don't want to know what's its value in 1 year or 2 years? What if you want to know what's the rate of depreciation? Meaning, how fast is it losing value? Well, have you heard that if you lose the majority of the value of your purchase, let's say of a car, within the first year? Maybe you've even heard how much you would lose just as soon as you drive it off the parking lot, right? So you would expect the rate of depreciation, meaning the rate that you're losing value, to be really high in the beginning, right? That first year you lost a lot of that $10,000 in value of that car. But as time goes by, right, for example, the difference between the value of a 10-year-old truck or an 11-year-old truck is normally it starts to maintain its value at a certain rate. Agreed? So let's read part B and part C and be done. It says find the rate of depreciation 1 year after purchase and the rate of depreciation 3 years after purchase. Based on what I said, I would predict that after 1 year purchase I should be a lot higher than 3 years. So that would make sense to me, but let's go ahead and finish this. So rate of something, rate of change, rate of depreciation, you should be thinking derivative. So part B, part C, I need V prime to do that. All right, well, I'm hoping you are starting to get pretty decent at chain rule. So, but let's go ahead and rewrite that. So before I write V prime, let's rewrite V. So first thing I could do is rewrite this as 10,000. Please allow me to do this in one step. I'm going to get rid of the radical, square root of t plus 1. I'm going to write that as t plus 1 to the half. But at the same time, I'm going to bring all of this up to the numerator. So it was t plus 1 to the half, but it's going to turn into the negative 1/2 when I bring it up. All right, this whole thing is brought up here, and I change the exponent from positive 1/2 to negative 1/2. Okay, so I've rewritten V. Now let's take a derivative. So V prime, I'm not going to go through all of the U, F of U, F prime of U. I just want to go ahead and get to what it would look like. So this would be 10,000 times negative 1/2, so that's negative 5,000 times t plus 1. And if I have negative 1/2 and take away, if I owe you 50 cents and then borrow another $1, I now owe you $1.50, or 3/2. Okay. So let's just clean that up. Oh, that's going to be negative 5,000. Get rid of the negative exponent. So that will be t over t plus 1 to the power of positive 3/2. Okay, all the heavy lifting is done. There's your rate of change. So part B says after 1 year. So V prime of 1. C is after 3 years. How much value are you losing per year? So V prime of 3. Okay, so I have v prime of 1. Again, you should double check this arithmetic, but I'm getting negative $1,767. And for v prime of 3, I'm getting negative $625. All right, and those are in dollars per year. That's in dollars per year. Okay, now the negative makes sense to me because, I mean, when I start driving my new car, it's not, unless I've missed something, it should be losing value per year. And so the negative numbers, they coincide with what we would expect. And notice that for this machine, it's losing value it's losing negative $1,767 per year after 1 year. But that machine is only losing $625 per year after 3 years. Okay. So thanks for your patience. I know these videos can be long and the material can be tough, but kudos for sticking with it. And I just know you're falling in love with this subject. I can feel it from the other end of your computer. And I will see you in the next video.